going with. To the cloud. So we're going to focus on the first three confidence intervals. All right. One population mean where sigma is known, one population mean where sigma is unknown. Sigma, again, is the population standard deviation. All right. So a case where we know the population standard deviation and a case where we don't. All right. And you know, we tend to oversimplify the verbiage here, where we say we know the population standard deviation. It's not always the case that we know it, but sometimes we could reasonably infer it. You can kind of look at a situation and say, I have a sense that it's not going to be a very widely dispersed data set, be tightly compressed. Right. So then you would assume a small standard deviation versus a large standard deviation. Right. So there's a lot of just kind of background information here. But what really we want to latch onto is part of this definition: a confidence interval for a population parameter is an interval of plausible values for that parameter. Right. So a parameter, just as a reminder, we talked about this early on, but we just kind of took it for granted after the fact. A parameter is a measure of a population. All right. So an example would be something like a population mean, or a population standard deviation, or a population proportion or percentage. All right. What we're going to do is estimate with a certain degree of confidence. All right. So for example, like 95% confidence. All right. What that tells us is that if we, I'm just basically going to rehash what this sentence says here, but if we were to take 100 samples, then we would expect about 95 of those to capture the true population parameter. Or in this case, we're going to start off talking about mu. All right, mu is in the population mean. All right, which would mean that about 5 of them would not capture. All right, so again, mu is population mean. I mean, we've talked about this plenty, but the whole idea behind the study of statistics is to be able to make inferences about a population. So you know what's happening on the small scale. How does that project out to the world at large, to the wider universe, or the whole world even sometimes, right? So what would happen is, and we did this in the third tech assignment, you create a sample. That sample may give you a measure that's pretty close to what the population mean is. All right, we found sample means. We did it 10 times. We found sample means. Some of those sample means are probably pretty close to the population mean, and some of them probably weren't. Right? What this is saying is that if we create intervals involving sample means, they're going to fluctuate depending on the sample that you select. Some of them are going to be more extreme than others, but in general, they're all going to be somewhat centrally located. The percent or the number out of 100 that capture the actual population mean dictates the confidence level. All right. Ideally, they would all capture the population mean, in which case you could be really, really sure where that population mean is. But it's also possible that none of them capture it, in which case you just chose some pretty bad samples, right? Or pretty extreme samples. I'm saying out of 100 samples, but there's no restriction. You could have 1,000 samples if you want. Right. So if the first 100 samples don't capture the population mean, then maybe you need to do like 20,000 samples, or actually 2,000 samples. But the bottom line is, if you want 95% confidence, you're going to want to have 95% of the samples that you select having intervals that capture the mean, right? That's the most abbreviated description of confidence that I could give, all right? Because it's really one of the frustrating concepts, because really you get further and further into this course, and the more, really the further you get, the more you have to take on faith. And here's a formula. Why does it work? Well, because of calculus. You're like, oh, okay, well, I don't know calculus. All right, so just please believe me that the formula works. I mean, it's frustrating, but it's the nature of things. It's the reason why you're able to take a statistics course without having taken a calculus course first. All right, so it's sort of the trade-off. But we'll dive right into an example, because yeah, there's a formula here. It's a good looking formula, but the NumWorks calculator handles this very, very nicely, right? And I'll show you what I mean by that in a sec. Right, the example, the average price of 40 recently purchased Westchester homes, taken via a simple random sample. By the way, this example I created about 10 years ago, so it's completely outdated, but we'll just go with it. Assume that the true standard deviation of Westchester home prices of homes recently purchased, circa 2010, is sigma is equal to 60,000. All right. So for a confidence interval, regarding the population mean, so mu for population mean, where we know the sigma value, we're going to use the Z interval. Although that's what the TI calculator calls it. We'll see what NumWorks calls it in a second. So for a confidence interval regarding the population mean, where we know the sigma value, we use a Z interval. All right. So the way you find that is by hitting the home button, go to inference, all right, so we're home, inference, hit OK. You'll see a bunch of options. The one we want is the intervals. And you see below that, it says confidence intervals, so it's kind of nice. Gives you a little reminder. Although the word interval probably is enough, but you never know. All right, we're going to go for one mean. And in fact, everything we do in this lesson is going to involve one mean. So these first few steps are going to be the same for everything we do. So one mean. And then you have a choice of T interval or Z interval, right? So we're going for Z interval. Definitely going down the rabbit hole here. So, but everything that we have in the problem has a place in this menu. All right. So the sample mean. All right. So SRS, simple random sample. So that makes this a sample mean. All right. They told us sigma, and we're talking about 40 recently purchased homes. So that's the N value. Then they say 95% confidence. So that's my confidence level, 0.95. All right. So everything has a home here. If you hit the clear button, well, the backspace button, it wipes out whatever in that that first field. So, or whatever is in that first field. So 730,000. Hit that little backspace button. 60,000. And 40. The default is 95 or 0.95. You might have to do a 90% confidence interval or a 99%, in which case you make some slight adjustments, but that should not be the difficult part of any of this. All right. Then you'll go to next. So I'm going to say input values. Go to next. Go to next again. They have useful information here, but since the calculator is going to do all the work for us, we could just skip past that. And then once I get to that last menu, it's going to give me the 95% confidence interval. All right. So right at the bottom, it has the plus or minus, but actually I want to be able to mark this up. So let me just do something real quick. Oops, I hit Siri. Sorry, Siri.
I'm sorry.
It was my fault. Copy and delete. Paste. All right. So these two numbers here, this one and this one, make up the confidence interval. All right. So what we do as a final answer is we take these two numbers and put them in brackets. So my 95% confidence interval, which I'll abbreviate CI, is going to go from 711,406 to 748,594. But we always include a conclusion sentence. You know, the old way of answering word problems. You know, like the question is presented in words, so you answer the question in words. You know, it's along those lines. But we follow a particular template, and that is, and it's very specific. So there aren't really too many ways that you could vary from this. So it should be easy enough. What we say is we are always 95% confident that the population mean price, okay, we always say what it is between, these are dollar amounts, so 711,406 and 748,594. All right. So I'll highlight the things that'll actually vary from problem to problem. It might not be a 95% confidence interval. It might not be related to price. And so therefore the units might be different. But everything else, that template should be the same. All right. So it could be, we are 99% confident that the population mean weight of buckets of ice cream is between 1 and 2 pounds. You know, it's always going to change based off the context of the problem, but the structure of it will always be the same. All right. Now, if you needed to make an adjustment, let's say you wanted to do 99% confidence instead of 95% confidence, you just hit the little back arrow there and just change that 0.95 to a 0.99, depending on the problem. All right. So structurally, in terms of the approach that you take on the calculator, very, very straightforward. You just got to know which menu to get into. Right. So if I wanted to do 0.9, 90% confidence. There you go. right? So all the magic is happening behind the scenes, which is great. It's great and it's frustrating, right? Great because it's very user friendly. It spits out the answer. Frustrating because at this point we don't really truly understand what we're looking at until you really start thinking about sampling, pulling samples of a variety of sizes, and seeing what sort of intervals might emerge from each individual sample, right? But that's the case where the population standard deviation is known. If the population standard deviation is not known, right, so that's the next one. We're going to do a lot of the same stuff. And in fact, process-wise, I'm just going to copy paste a lot of this. Because we're still trying to find or trying to estimate a population mean, but we don't know the population standard deviation. All right. So for a confidence interval regarding mu, where we do not know, where we don't know the sigma value, we use a t interval. Still home inference intervals, one mean, but we go for t interval as opposed to a z interval. But we do pretty much everything else the same way. Right? So same structure, same, really very much the same in terms of the buttons you press. It's just we're using a slightly different function. Right? 25 students are selected at random to be included in a study related to fat intake of high school students from the sample of 25 randomly selected individuals. So that's my n value. The mean and standard deviation were 52.771. Now this is for the sample specifically. So this is my X bar. And this one is my S. S for sample standard deviation. We're still looking for 95% confidence though. So go back to my home. Too good for your home. I'm going to go to inference. I'm going to select intervals. All right, so intervals. I'm going to select one mean. This time it's going to be the t interval. But in terms of what I type in, it's pretty much the same structure. All right, so clear this out. Type in a 52.771. Clear this out. Type in a 7.125. Clear this out. Type in a 25. And everything is the way I would like it to be. And, you know, like in terms of what we actually write out, honestly, if you look back at that previous page there, and I'll zoom out in a second, but if you, or zoom in, sorry. If you look at that previous page, that was a whole lot of writing, but ultimately all I would need from you is this stuff. All right. The rest of it is just for instructional purposes. So in this case here, yeah, we're doing all this stuff, but it's happening behind the scenes, which makes it a whole lot nicer because we don't have to write any of this down. So go to next. Next again, and you have your confidence interval.
So did I hear a Happy Gilmore reference sneakily snuck
You
in there?
sure did.
Okay, I thought I was like losing my mind.
No. What's the matter? You're too good for your home?
Exactly. Oh, man.
What a movie. Stands the test of time.
It really does.
I can't say the two or three comments that come into my mind immediately, but one involves Bob Barker. The price is wrong, and then I can't say the rest.
That's right. Oh, man. That's definitely on the list to watch in between semester breaks.
Exactly. I mean, if that goes for anyone, if you haven't seen that movie, it's
Gotta.
such a good one.
Classic Adam Sandler.
Seven, 1, 2, 1. All right, so this would be our confidence interval. Now, again, we're just going back to what I was saying before. We're going to structure our conclusion the same way. We are 95% confident, but it's a question of what we are 95% confident about. So we are 95% confident that the population mean and, just a very quick description of what we're talking about. It's fat intake. Is between these two numbers, but in terms of grams. So 49.8299 grams and 55.7121 grams. All right. Now, the purpose of this is not to draw any conclusions in terms of, like you're a researcher and you're trying to, change the world, that kind of thing. It's more like, just the facts. All right. So we're 95% confident the population mean fat intake is between these two numbers. Let the researcher actually do something with that. All right. We don't need to editorialize at any point. Like, oh, that's an awfully high number, or that's not that bad. Like we don't get into that. We just state the facts. All right. So we know that this approach is used in any case. Well, we now know that this approach is used in any case where we're trying to find a confidence interval involving the population mean, but we don't know the sigma value. All right. And honestly, the way most of the questions have to be structured, it almost always has to be overt if the sample population standard deviation is known. It's almost like it's a violation of the way people speak. Like assume that the true standard deviation of Westchester home prices of homes recently purchased is sigma equals 60,000. Nobody speaks that way. It might say the population standard deviation is known to be 60,000, but any other instance where they talk about standard deviation is most likely related to the sample. All right. In this case, we know it is because it says from the sample of 25 randomly selected individuals, the mean and standard deviation are this and that. Right. So they're spelling it out for us. All right. So it's all in the problem. It's just a question of how you read it. Like just read it carefully and you're good. And so the last one, and really the last topic in the whole course, is the match pairs T procedure. I'm going to go with classic as the word of the day. Classic, as in the movie Happy Gilmore being a classic. Perhaps even Christmas Vacation, if you haven't seen that one.
That's an excellent one. There should be a list of what's required watching.
Yeah. You know what? That's a good idea.
Right? Get a list of
like coming into any of my classes, it's like required reading.
Required.
I got to do the reading. Oh, you mean the textbook? No, you told me to watch Happy Gilmore. And that's the way to do it. So match pairs T procedure. Well, it's a match pairs T design. It's dealing with before and after cases. All right. So I mean, you can see it. It's the before and after is coming up over and over again. All right. But the idea is that there are two pairs or paired data that make sense to be grouped together. All right. So most likely a before and after. So if you ever see one of those hair growth commercials, like the guy that doesn't have any, and then the guy who's got like a full head of hair, and they're supposed to be the same person, but they're not really, because you can tell. Weight loss commercials, like so and so lost 3,000 pounds. You're like, I didn't even know anybody could have that many. But like things like that, you can tell the person's Photoshop. It's bottom line is you're looking at, oh, what another good one is the what's it called? OxyClean. They have the ones where the car is like
I
cloud.
think that guy died, by the way.
Oh, what's his face? Oh,
That, wasn't he like the spokesperson or something, or owned the company, or
yeah. I know who you're talking about. They did a whole South Park thing on him.
exactly.
But yeah, like those kind of commercials where it's like, the car is all like dusty and cloudy, the paint job and everything, and then they do the OxyClean and it's all clean afterwards. That would be a case of before and after. Right. So we're going to look at something that's unrelated to any of that. But yeah, that's the idea. Like if you can get a sense of before and after in whatever question you're being asked, then it's usually easy to pick out that you're dealing with a match pairs distribution. The good news is it's exactly the same procedure that we just used. All right, except we usually have to do some data work beforehand. All right. So what we need to figure out is the difference between the before and after values. So the scenario here, a pharmaceutical company claims that it developed a new medication for lowering cholesterol. It takes 15 random subjects who have high cholesterol and measures their cholesterol level before the study, and then 12 weeks after receiving the new medication. Right. The units are given, construct a 95% confidence interval to estimate the average difference before and after taking the new medication. All right. So we can handle this pretty easily. I mean, finding the difference between two values should not be the problem, although the calculator will handle that for us. What we need to do is we need to find the mean and standard deviation of the differences. So whatever the difference is, we have to find the mean and standard deviation of that. So I need the mu sub d. Oh, actually, this is a sample, sorry. X bar sub d and S sub d. All right, D for difference. All right, so if you subtract them manually, that's fine. If you do it with the calculator, that's fine too. Either way, we need these two numbers. All right, however you get it, short of cheating, of course. So I'm going to go into the home menu. I'm going to go to statistics. So home, statistics. All right, we're going to go to data. All right, I want to put these values in, which is probably the most challenging part of this whole thing. On value view one, I'm going to clear that out, confirm. and just start typing away, right? So 287, 290, 310, 305, 289, 281, 320, 299, 300, 288, 293, 281, 311, 290, and 287. All right, so that's my first list. All right, my second list, so the before values go into value V1. The after values will go into value V2. Right, so we don't put anything in the frequency list. All right, frequencies are just telling me how often the numbers I just typed in occur. All right, so 230, so value V2, 230 twice, 258, 251, 230, 220, 270, and so on. All right, so get all those values in there. Then in value V3, so in value V3, I'm going to select OK or execute. I'm going to go over to value V3, like right on it. All right, so I should say on value V3. I'm going to hit, oops. I'm going to hit OK and select fill with formula. All right, so that's my second option there. And then I'm going to type in V1 minus V2. So type in V1 minus V2. So I hit OK. And if you go down the list, sometimes you have something that's pretty close to what you want. This last one here is, it's not quite, but it's got the right ingredients. I need V1 minus V2. So I can select this one, right? So I'll say select V1 plus V2, and then change the plus to a minus. So I just hit the little left arrow, then the backspace, tuck in a little minus sign there. And that's why they give those templates, so that you can make slight adjustments. But if I hit OK in V3, it's going to include all of the differences between the values in V1 and V2. Now, you may look at it and say, well, it's only 15 values. I'd rather just subtract it. Okay, if it's 30 values, 50 values, you probably want to have technology handle that for you. All right, so 57, 60, 52, 54, 59, 61, 50, 59, 56, 53, 63, 61, 59, 60, and then 51. All right, so these are the differences. We'll take this as a typo, throw the S on at the end there. All right, but what I need now is the sample mean and sample standard deviation of this. But NumWorks will do that for us. So I'm going to go to stats and look for X bar and S for value V3. All right, so I go up the line here over to stats. You see the default there is V1N1. I want to go right until I get to the one that I'm looking for, V3N3. So value V3N3. Go down the line until you find the X bar. That's 57. Poor quality 5. And 4.0883. All right. So this is the setup. This is getting, the last couple of problems that we did, they had the mean and standard deviation given to us. Here, we needed to figure it out first. All right. There are 15 values. So I know the N value is going to be 15. And we're looking for 95% confidence. So now I'm ready to go into my inference menu. All right. It's the same inference menu that we just used. So home, inference. We're going for one mean. Well, intervals, then one mean.
Which interval? T interval?
It's going to be the T interval. Yep. And then we put our new numbers in here. So the 57, the 4 point whatever, 4.0883, and the 15. And it's again 95% confidence. So it's a whole bunch of next. So next. And it gives us our confidence interval, which is going to be 54. So my 95% confidence, my CI, is going to go from 54.736 to 59.264. And then we state our conclusion. All right, so we are 95% confident that the population mean difference. All right, so this is a key departure from what we just did. Difference, because we're not actually finding the population mean. This whole table here was to find the difference between the before and after values. So the population mean difference in cholesterol is between 54.736 milligrams per deciliter and 59.264 milligrams per deciliter. All right. So it's between those two numbers. Now, the conclusion, again, what I was saying before is we're not really interested in going beyond just a statement of the facts. But if you're interested, if you show a positive difference from the before to the after, that means that on average, the before numbers are bigger than the after numbers. All right. If the before numbers are statistically significantly bigger than the after numbers, that's showing a decrease from before to after. You went from bigger to smaller. The difference between bigger and smaller should be positive. Right. So that's showing at a statistically significant level of 95% that this medication must be effective. All right. Now, if they're both negative, if the both bounds of the interval are negative, that would show an increase, because that would mean before is less than the after. All right. So before grew to become the after, that would be an increase in cholesterol. All right. Now, if one bound is negative and the other is positive, that's inconclusive. All right. We can't make a determination of increase or decrease. All right. But because they're both positive, that's showing that there is a statistically significant decrease between the before and the after, specifically from the before to the after. All right, which is pretty useful stuff. All right. So in terms of new content, that's it. There's nothing beyond this. Let me shift gears here for a minute and take you over to the practice test. So I'm going to stop this recording.